Now, when we go to high school and we learn science, when we learn how to think rationally, we learn critical thinking, we learn logic and mathematics, we learn stuff that's presented as though it's all one thing. We learn this sort of monolithic block, particularly in science. You learn the scientific method. This is invented. They all had to be thought up. But it wasn't until a whole bunch of different things came together that we started having real modern science. And what I'm going to talk about this week is an important chunk of philosophy, the epistemology and ontology of John Locke, particularly his epistemology. It's an important piece of philosophy, but there's also an important piece of science, a piece of science that is so important, so fundamental, most scientists don't even talk about it. You could go through an entire course of high school physics or high school chemistry, or the history of science, or maybe not the history of science, but you can go through a bunch of science courses without ever hearing of this thing. But it's fundamental. Without this principle, we don't have science. Science really isn't possible without this principle. It's that important. Okay, how many of you guys have heard, before this class, before the reading for this class, have heard of Occam's razor? One. So that's how fundamental it is. It's so fundamental, it's like breathing. You have to breathe to go into a science class, but nobody talks about it. It's that fundamental. And it's that weird that only one person's heard of it, because it's so important. So, I'm going to tell you what Occam's razor is, and then I'm going to show you, give you an example of how it works. And then I'm going to show you how it was used in philosophy by John Locke to move epistemology forward. That is to well, let's put it this way. Modern epistemology, like science, would not be possible without Occam's razor. Thought itself, thinking stuff up, coming up with good ideas, having accurate and useful descriptions of the world, really wouldn't be possible without Occam's razor. Thank you. Now I'm going to put up the most technical definition of Occam's razor. By the way, it doesn't matter how you spell it. ask this for you. When you have two or more equally adequate explanations, now, the easiest way to think of this is in terms of science, scientific explanations. When you have diversity of materials, where you can have things like sulfur and carbon and granite and all different other kinds of matter. The modern scientific explanation is that there are elements, hydrogen, oxygen, carbon, lithium, uranium, and that these elements come in atoms. It's the smallest unit that can be the same element, and we get all the other stuff by combining atoms, combining elements, modern chemistry, right? The explanation for the diversity of life on Earth, starting with simple replicators that can replicate themselves with more almost perfect accuracy. Descent with modification, because replicants have slight variations from their parents. And that has a biochemical basis. So there's these explanations. Now, an adequate explanation is one that doesn't contradict the facts, doesn't leave anything out, and it's one that gives us a basis for future research. Evolution through natural selection is actually the most fruitful theory we've ever had scientifically. It's also pretty much the best confirmed. It's a rock-solid scientific theory, and it has applications outside of biology. And it's very rare you get a theory that will have applications outside biology. But the theory has been applied to sociology, psychology, brain development. You've ever heard of neural Darwinism, brain organization, and computer programming. The theory has proved out in all those domains. So it's been very fruitful, and that's part of being an adequate explanation. If you have an explanation that's fruitful, that is better than one that isn't fruitful. So when you have two or more equally adequate explanations, or roughly equally adequate explanations, for the same thing, you should choose the one that requires the fewest new theoretical entities. The one that requires us to believe, let's take out mu. The one that requires us to believe in the fewest things that we cannot directly observe. Evolution through natural selection just requires us to believe in genes and mathematics. We know mathematics exists, and we know genes exist, so there's not much in the way of theoretical entities. So that's the sort of very precise definition. Here's a less precise. It's important to remember, adequate explanation fits the facts. Occasionally I've had exam answers which read Occam's razor could be bad, because what if the simplest explanation is wrong? I'm not talking about wrong explanations here. If you know the explanation is wrong, it's not an adequate explanation. So it's the simplest explanation that fits the facts. Or out of two or more equally adequate explanations, pick the one that requires the fewest theoretical entities. Do not write down that Occam's razor says, always pick the simplest explanation. It doesn't. It does not say always choose the simplest explanation. And there's an issue with what counts as a simple explanation. You guys ever heard of gremlins?
Yeah.
In World War II, aircraft started carrying sophisticated electronic equipment. Right? This was more than just radio. They carried radar, radio detection, radio directional equipment. They also carried the radios and electronics in the bomb sites. And this stuff did not work perfectly. So you imagine you're a flight engineer on a bomber over Germany. There's anti-aircraft fire coming up at you, things are exploding, and your radio won't work, or your direction finder won't work, and you can't figure out what's wrong with it. In the 8th Army Air Force, whenever there was something wrong with the radios, they said it was gremlins. What's wrong with the radio? Gremlins again. Now, I'll ask you, is this a simple explanation? Yeah. Why? What's simple about it? It's just one word, right? But that isn't simple in this sense. It's not simple in terms of being an adequate explanation, because in order for gremlins to be the explanation, you have to believe that gremlins exist, which means you have to believe in entities that can be completely invisible by some means. They're undetectable. You cannot look around and find gremlins. They cannot be kept out of electronic equipment. You can't put a box around the electronics and keep the gremlins out, so they can pass through at least wire mesh. They can affect electronic equipment without affecting it physically, without making physical changes to it. Right? Because they don't open the box and find wires missing and wires disconnected and things taken out and things broken. They open the box and it looks just the way it did when they closed the box. So you have to believe in something that contradicts everything we know about animals, about biology, about intelligent beings. According to our best information, how many different types of intelligent being are there, of fully intelligent, willed being are there on this planet? There's one. There's us. So believing in gremlins actually requires you to believe a very complicated thing, a thing with a lot of details. And not only is it very complicated, you have to believe in new laws of nature. If you believe in gremlins, you believe in a world that does not make sense anymore. These are things that don't make sense according to our standard model of physics, of biology, of psychology, of ethology. This violates all the rules. This violates everything we've understood so far. So if you're going to believe, if you want this to be the explanation, you have to explain how it is these things can exist. Well, they radically contradict all the things. And if your response is, well, they have these powers beyond human understanding, you haven't explained anything. Another thing about gremlins is It turns out saying it was gremlins is just the same as saying it just happened. Because when I say it's gremlins, I don't give you any information. You can't do anything with it. Compare it's gremlins to it's a loose wire on the condenser. I say it's gremlins. What can you do? I say it's a loose wire. You go, oh, and then you tighten it up. Think about when your car goes wrong. You ask the mechanic to explain it. He says, I know exactly what it is. Magic fish. Magic fish got into your car and made it not work. Great, how do you fix that? I don't know, but I do know it was the fish. If someone offers an explanation for something, if that question has no consequence, if that explanation has no consequences in terms of future behavior, it's not an explanation. Now, on to the scientific example. Oh, any questions? Again, I want to emphasize, without Occam's razor, science really isn't possible. In fact, knowledge isn't really possible. All right, now, in the Ptolemaic system of astronomy, Ptolemy is a long time ago. In the medieval period, they still followed Ptolemaic astronomy, which held that the Earth is the center of the universe. And around the Earth orbits not only the Moon, but also Mr. Sun. Now, here's the bit I find hard to explain. You guys know what the plane of the ecliptic is? The plane of the ecliptic is basically a line across the sky in which along which all the planets move. So, if you see 3 planets in the sky at the same time, they will describe a straight line. You can't have one up there, one down there, and one over there. If you've got 2 planets in the sky, any other planet is going to be in line with those 2. That's because all the orbits of the planets in our solar system are flat. They're all in the same plane. So, planets wander, but they all wander along the same track. Now, when the ancients, by the way, another interesting quirk of science, scientists no longer believe in astrology, right? Astrology is just not part of science. But astrology made an important contribution to science, because without astrology, we would not have astronomy, because all the major astronomical observations of the ancient world were taken pretty much by astrologers. and at least a lot of the funding for science in the ancient world came from astrology, because a lot of astronomers could not make a living as astronomers, but they could make a lot of money as astrologers. So a lot of observations were taken for astrological purposes. And as people made these observations, they found that planets only moved in the plane of the ecliptic. They only moved on one track, and they didn't move constantly. Right? They did not move at a constant velocity. Instead, they would move along, and then suddenly they'd start moving backwards, and then they move forwards again. They did what's called retrograde motion. They'd move, generally they'd be moving around on the plane of the ecliptic, but every so often they'd stop and then move back and then they'd start again. So how to explain retrograde motion? Let's take the planet Venus. Now,
That's a stupid question, but isn't the yellow thing the sun?
yeah,
Why is the sun going around the Earth?
that's what they thought back then. To them, that's what made sense. This is the Ptolemaic system of astronomy. Right? We see the sun moving around us in a big circle. We see the planet Venus moving around us in a big circle, except every so often Venus changes direction, moves the other way back of it. It's like Venus drops its keys, notices the loss, goes back, picks up her keys, moves on. So, planet Venus moves backwards part of the time. So what Ptolemy did, was came up with a brilliant mathematical idea that Venus does not orbit in a circle around the Earth. Rather, Venus describes a little circle in space, or a big circle in space, I'm not sure why, but it's easier to draw a little circle. Venus goes around in a circle in space, and that circle goes around a mathematical point. And I draw those the four little lines there with a little gap in the middle, because there's nothing at that point. It's just a mathematical point. It's a piece of empty space that is described mathematically, just like this point in space here. See, nothing here except some air that's moving around through it. But you can imagine that point. But you can imagine the exact mathematical center of this room. It's not a thing, it's a mathematical point. So there's nothing there. But that non-existent mathematical point goes around the Earth in a circle. A real circle, not like what I draw. So, sometimes Venus is moving faster than the point, sometimes it's moving back. I guess the epicycle would be like a big one, but I don't know. I'm not a mathematician. So, Venus moves in a circle around a mathematical point that moves in a circle. Ptolemy explained retrograde motion by epicycles. And his model could be fitted to the data by adjusting you can adjust these epicycles. If it gets Venus almost all the way there, but not quite, maybe you'll put another epicycle in the system. You can have Venus orbit a point that orbits another point that orbits another point that itself goes around the Earth. So, all motion is circular because the circle is the perfect motion. The circle is a perfect shape. All motion in the heavens is circular, and everything goes around the Earth. That's the Ptolemaic system. Now, hold on. How many of you spotted my non-deliberate mistake? Who came up with the heliocentric system? I just wrote it on the board. Copernicus. Okay. In the system of Copernicus, there's Mr. Sun in the middle. Around Mr. Sun go the planets. Mercury. Not sure what Mercury is. Venus. Earth. Luna. Jupiter. Saturn. All in circles. Now, how does the Copernican system explain retrograde motion? Well, some of the time we're gaining on these outer planets, and some of the time we're leaving them behind. So we sort of like come up and past them. So sometimes they look like they're going the other way relative to us. They're really not. Now, mathematically, in terms of fitting the data, in terms of fitting our observations of the world, right? Science is observational. You have two theories, right? You have two theories and you compare both of them to the observations. You look out at the world, you make predictions based on the theories. The moon goes around the Earth, but everything else goes around the sun, and we're kind of in the middle. The theory of Ptolemy. Earth is in the center, everything orbits the Earth in systems of epicycles. Now, when you compare the results of Ptolemy's system to actual observations, and you see a divergence, you see that Ptolemy doesn't predict exactly the right outcome, exactly the right observation, you can adjust this system by expanding or contracting the epicycles or by adding a whole new epicycle. Right? Round like a circle in 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 a circle that goes around the Earth. In the system of Copernicus, you do not have epicycles. There are no epicycles here. Instead, you have exactly circular orbits. What can you do when the data doesn't fit, when the observation doesn't fit the prediction? Now, the question I want you to think about now. Historically, when people compared the predictions of the two systems, which system made the better predictions? If Copernicus and Ptolemy were to have a bet on the position of planet Venus at midnight tomorrow night, if they were to make a bet on where Venus is going to be on the plane of the ecliptic, they're going to make a bet over here. Here's the plane of the ecliptic. Here's Ptolemy's bet. Here's Copernicus's bet. Who's going to be right? Who's going to be closest? Who's going to win the bet? The money goes to the person who predicts the position of Venus with the greatest accuracy. Which of these theories is going to make the best prediction? Say again? Copernicus? How?
Because the epicycles could be wrong.
Well, when the epicycles were wrong in the past, they adjusted them.
Yeah, but I mean, so are we talking about after adjustment or?
Yeah, we're talking, when the theories are fully developed at the time of say, John Locke. That's right. Ptolemy made the best predictions. With that set up, what kind of answer can I give you? Think about it. I'm setting you up here. We expect Copernicus to be better, because this is the theory that's closest to what we believe now. But we didn't get there simply. We didn't get there by looking at Copernicus and saying, oh look, better predictions. No. Every time Ptolemy lost the bet, he could change his system. Copernicus could not change the system. He did not have epicycles. All he could do was move the planets back a bit, speed them up or slow them down. Never matched the observations with anything like the accuracy of Ptolemy. Never matched the observations. Now, scientists at the time, or rather philosophers, natural philosophers at the time, like Galileo and René Descartes, knew this. They knew all about the competing systems. Which system did they go for? And what rule did they use to go for that system? If we go with what system produces the most accurate observations, where do we go? Ptolemy. If we go with Occam's razor, where do we go? We go with Copernicus. Copernicus has no epicycles. Basically, the predictions given by Copernicus were accurate enough to be interesting. They were accurate enough for people to say, you know, Copernicus has got something here. This makes more sense. Also, putting the sun in the middle, the big hot body, that seemed to make sense to a lot of people too. So this one just seemed to make more sense, and it didn't have the damned epicycles. A mathematician or a natural science philosopher looks at these epicycles and says, I don't see how that can make sense. Why would something move in a circle around a point that moves around a point that moves around a point? How could that system work? It doesn't feel natural. It feels constructed. Now, the other thing, the thing that I think that made the difference between the two theories for most scientists was that if you go with the Copernican system, you have a big problem. You have, why doesn't it match the observations? What else is going on? Okay? You look at it and go, this is not It's close to making sense, but it's not all the way. Maybe there's something else here. Maybe there's some other force or some other entity, or there's some little tweak we can give to the system that will make it come out right. The Copernican system gave interesting problems. Gave you something to think about. The Copernican system presented an interesting puzzle. How about making the Ptolemaic system better? How about making the Ptolemaic system closer and closer to the observations? If you've ever found yourself really interested in a math problem, then that's kind of the feeling people had when they looked at the Copernican system. I want to work this out. If you've ever had a series of math problems that are kind of stuff you've done before 100 times, and you just got to go through them over and over again, and you're just going to grind through these bloody exercises, doing the same thing over and over again with different values, then you have some of the flavor of Ptolemaic astronomy. It was boring. And of course it always came out right. It couldn't ever be wrong. And that's another thing that's wrong with it. It's unfalsifiable. No matter what the observations, they could add an epicycle. It was just math. It was just accounting. Nowadays, in science, we look at a theory, and if the theory is unfalsifiable, if we cannot imagine an observation that would prove it wrong, it's thrown out. It's useless. It's unscientific. How to get into the casings, how to get in and out of aircraft. Right? How do they have these powers? They just do. How would you prove that gremlins don't exist? They're invisible. And they can and if it's a digital camera, they can mess it up too. So if your camera goes wrong, it's gremlins. And if it doesn't go wrong, the gremlins passed you up this time. Well, if someone says, I can explain this with an untestable entity, an entity whose existence you could never prove or disprove, they've given you an entity in which you have absolutely no reason to believe. If you look at it another way, oh, gremlins is the perfect explanation because you can't prove it wrong. Excuse me, if you told me it cannot ever be proved wrong under any possible set of circumstances, you've just told me it is wrong. If it's unfalsifiable, it's wrong. Period. We don't even need to continue thinking about it. We can forget it. Certainly as a scientific explanation. So, what would have happened to astronomy? What would astronomy be like now if we had gone with Ptolemy? What would astronomy be like now? Well, it would be like this. It would be boring and tedious. No one would be interested in it. Because anytime you have an observation that doesn't fit the facts, you just fix the epicycles. No one would be paying attention. except astrologers.
Would we have confidence in that?
I don't think so. Let me tell you about Copernicus and astronomical progress. First thing is this guy called Johannes Kepler came up with the idea that the orbits are not circles, they're ellipses. Now, at the time, this was almost considered blasphemy. If he'd come up with the idea a couple of hundred years before, they might have burned him at the stake for suggesting the heavens were less than perfect. I don't know how that's okay. He also came up with his laws of motion. Kepler's laws, a mathematical law saying that the radius of an orbit sweeps the same area in the same time every time. So when a planet is further from the sun, it moves faster. When it's close to the sun, it moves slower. It's actually related to the period of the pendulum, which is pretty cool. Well, a mathematician called Sir Isaac Newton looked at Kepler's laws and said, wait a moment, if we calculate the masses of the planets and factor that in, we can make a model that predicts Kepler's laws. Newton's laws of motion and Newton's law of universal gravitation explain the apparent motions of the heavenly bodies with very high precision. Not absolute precision. Probably better than Ptolemy at this time, but I don't think anyone cared about Ptolemy at this time. Newton's laws gave a universal explanation for the motions of the planets. Newton's laws made the observations make sense. If the planets are in the situation they are with the masses and velocities they have, they will continue to move like this. And Newton gave very precise predictions. But not perfect. There was an anomaly in the orbit of Saturn and an anomaly in the orbit of Mercury. By anomaly, I mean Saturn didn't quite move the way Newton said it would. The Earth moved perfectly according to Newton's laws. Venus and Mars, perfect. Saturn, there was a problem. Two separate groups of mathematicians sat down with this problem and figured, okay, let's assume that Newton is right. What could account for the anomaly in the orbit of Saturn? Well, if there is another planet out there, a planet that's too faint to see, or too faint to see normally by inspecting the sky, too faint to see with the naked eye. If there's another planet out there, how big would it have to be? And how far away? In what orbit would it have to be in? So they plugged Newton's laws into the model, saying, let's try a planet here at this size. So, okay, that doesn't work. Let's try and make it bigger and closer, or smaller and further away. And then they found an orbit, a location, and a mass that worked. And they wrote to an astronomer and said, hey, if you point your telescope at this part of the sky at this time, you'll see another planet. And he did. And he did. The planet Uranus was found mathematically. position was calculated based on Newton's laws and the observed orbit of Saturn. Let's see Ptolemy do that. The Ptolemaic system was completely incapable of this kind of thing. And after carefully observing the orbit of Uranus, they found it had an anomaly, and from that they predicted the planet's Neptune. So 2 of the planets in the solar system were discovered mathematically based on Newton's theory of universal gravitation and the observed motions of the known planets. This is why Occam's razor is fundamental. Ptolemy and Copernicus both fit the facts. Ptolemy a bit better than Copernicus. But the Ptolemaic system was very complicated compared to Copernicus. So since both systems fit the facts, they went with the most simple system. If it had turned out there had been some fact that Copernicus really didn't fit, they would not have followed Copernicus. It's important to remember this is not always pick the simple theory. It's pick the simplest theory that fits the known facts. Fits the facts. Now, if you look at any scientific theory, any set of phenomena, the theory science goes with is the most simple theory that fits the facts. Because for any set of facts, you can come up with infinitely many theories. Theories are always underdetermined by the facts. But all the other theories are more complicated than the one we went with. Every other theory for observed evolution of plants and animals, for observed diversity of species, every other theory is either more complicated than Darwin's or fails to fit the facts. Darwin's theory is the most simple theory that fits the facts. Sometimes the most simple theory is still pretty damn complicated. Occam's razor turns out to be an important epistemological principle. It turns out we really can't claim to know anything unless we accept Occam's razor. All of our claims of knowledge about the universe, about the world outside our skins, are really based on Occam's razor. Think back to what we did with the card. I gave you 2 apparently adequate explanations for your experience. One, there is a real world and you're living in it, with all the complications of physics and laws and everything like that. And then there's the other explanation. You are a brain in a vat. You are a purple jellyfish being fed information to create a virtual reality Disneyland kind of experience. Okay, you're on an elaborate version of Star Tours. If anyone's ever seen the show Red Dwarf, anyone ever heard of Red Dwarf? Say again? Nothing to do with Travelocity. Red Dwarf. Red Dwarf is a British science fiction situation comedy. And in it, there's an episode called Back to Reality. we have like six seasons of this TV show, and then they have an episode where all the rest of the show up to that point was a video game, a total immersion video game. So you can imagine that the class is interrupted. There's a blinding light in your eyes. Someone takes a helmet off your head, and you find you've been in a really unrewarding video game. You know, Philosophy 2000. And you're a little old woman who lives in Pasadena. So that's an explanation for your experience. Is it a good explanation? Is it a simple explanation? No, because you have to explain how all this stuff can happen, and you've got to assume a whole new universe which you know nothing about. So it's not really an explanation at all. The reason we go with things as they are, because it's the simplest explanation that fits the facts. Now the same applies to philosophy. Rented a car, and Plato believed in innate ideas. And before Locke, lots of people believed in innate ideas, following either Plato or Descartes. Ideas come to you from before you're born. They're planted in your soul by forms, or by God, or by gremlins, or munchkins, or an evil robot with a mind control ray, or another pink jellyfish. Locke had a different idea. Locke said, well, maybe ideas come from experience. Maybe just two theoretical entities. In order to believe in innate ideas, you have to believe that the soul exists before the body, or before life, and you believe in some kind of imprinting mechanism that imprints ideas on the soul. And you have to believe that ideas can exist outside of a mind. That ideas, or at least templates for ideas, can exist outside of human minds. That there's some place of storing ideas, some reality outside that. You have to believe in some kind of idealism. None of which we have any independent evidence for. These are all theoretical entities, because the only reason we have to believe in these things is, how do you explain ideas if these things don't exist? The only argument for the existence of the soul, for pre-life imprinting, for external idea storage, for independent existence of ideas at all, for any kind of immaterial entity. The only argument we have at this point is ideas exist. I have ideas in my mind. Where did they come from? Occam's razor is called a razor because it cuts away unnecessary complications. Occam's razor is about cutting away ideas that we do not need. Locke is looking for a simpler but adequate explanation for ideas. Without Occam's razor, we cannot make this kind of progress. Notice that Occam's razor is a different criteria for acceptability from Descartes. Descartes' method of doubt said he was not going to accept any claim for which he did not have certainty. If the claim could be doubted, he would not believe it. Locke abandons this idea. Two reasons. Well, one reason is it doesn't work. The main reason is it just did not work. We need to try something else. It turns out we cannot have absolute certain knowledge of the external world. All we can know is definitional. Know with certainty is definitional knowledge, deductive logic. So we need another rule. And the rule we came up with, the rule that works, and it actually wasn't invented by Occam. I guess he kind of made it famous. But Occam's razor is the rule we use because if we have to choose between two equally adequate explanations, we go with the simplest explanation until we have reason to abandon it. Knowledge is always tentative. Science is tentative. It's funny. Science emphasizes the doubtful nature of knowledge. Science emphasizes fallibility, where you have ideas like the theory of evolution, the theory of quantum mechanics, the theory of relativity, the big theories of science. And people emphasize, well, we think this is true, but it might not be. We're just going for it because this is the best explanation we have right now. It is the simplest explanation that fits the facts. If something else comes along, I read an article now, they're thinking of throwing out the standard cosmological model. It's only been in place about 80 years, and they're thinking of abandoning it because they found facts that it doesn't fit, or the facts that it might be shown not to fit. Science is tentative, but every other claim of knowledge turns out to be more tentative. People who claim to have absolute certainty about the world usually turn out to be completely and utterly wrong. And they always turn out to have less certainty than they claim. Science is the most certain form of knowledge, and it is the form of knowledge that most emphasizes that it is uncertain. So the rule, let's only believe things that we can prove with certainty, is a terrible rule. It fails. We learn nothing by following that rule because we cannot get off the ground. We cannot go beyond cogito ergo sum. So we need a different rule. And this is the rule we went with. And the reason we went with it is because it works. Now, applying it to epistemology, we have a complicated explanation for ideas. If Locke can come up with an adequate explanation that doesn't have these theoretical entities, he can throw these entities out. But his explanation has to be adequate. It has to fit the facts. So on Wednesday, I will talk about Locke's explanation for ideas, and we'll see how close it fits the facts.